All right, so welcome to the second part of the Schubert seminar with Bill Graham telling us about irreducible characteristic cycles for orbits of some subgroups.
Okay, so finally, I think I wanted to tell you because it's somewhat useful for what I'm going to say later because I want to specify very clearly what clans we're getting these resolutions of. So maybe I should just tell you the monoid action is actually very simple to describe in this case. So again, V is going to be A1 up to AN, and SI is as usual. It's this transposition. And then V star SI is bigger than V if and only if. So, there's sort of two conditions. One is if there's a number involved. So 1A is AI and AI plus 1 are different numbers. And the mate of AI occurs for the mate of AI plus 1, or one of AI and AI plus 1 is a sign, and the other a number. Whose mate is on the same side of the sign. And in this case, in either of these cases, V star SI just switches AI and AI plus 1. And the other case is that AI and AI plus 1 are opposite signs. And in this case, V star SI changes these to a pair of numbers, to matching numbers. So it's all very concrete. Okay, so then just let me talk about resolutions very quickly then. So in general, what I'm going to do is essentially what Alan had said before. Forget about what I was being in G mod B, and so let's let GV be equal to KV dot B, and so XV the orb closure, and so XV is going to be GV mod B. And so then if this should be very familiar to anybody who's seen Bott-Samuelson type resolution. So if V star S is bigger than V, we get GV cross P cross B of PS mod B going on to G X V star S. And this is birational. For our G and K. In general, it could be 2 to 1, generically 2 to 1 in other types. And then, so we can iterate this. So what I want to consider the situation is, let's let I be a set of commuting simple reflections. And let's let X V naught be a smooth orbit closure. And so then what we get is a resolution. So under the assumption okay, so maybe I should back up for a second. So because these are commuting simple reflections, everything is very simple, but I want to look at the P of I be the corresponding parabolic. Wi is the corresponding file group. Wi is the long element. And so the length of Wi is just I here. It's very simple here. Okay, so what I'm going to assume is that to iterate this, what we need is assume that the length of V naught star Wi is the length of V naught plus I. So what this means is that simply is that V naught is less than V naught star SI1 is less than V naught star SI1 star SI2 and so on. So assuming that holds, we just iterate this process above and we get a resolution mu from GV naught cross B PI mod B. So I'm just putting all those little one-step parabolics together in this PI, which is a very simple parabolic because these are commuting reflections. And this is going to go to XV, where V is equal to V naught star of Wi. And I'll just call this ZV here. So this is a resolution of singularities of this particular orbit V. It's a resolution because XV naught is smooth. And so it's a very, of course, it's a very particular kind of resolution, and so there's some strong assumptions on this. So the question is, when is this small? And so Scott Larson actually answered when this is small. So this is small if and only if. So it's a condition that I'll state in a more abstract way, and then I'll state it very concretely. So for all y which are less than or equal to my original orbit V naught, I'll say strictly less than that, such that the orbit is of codimension 1. We have, if I take the length of y star Wi, this is equal to the length of y plus I. So this is basically saying something about the fiber dimensions over, basically like zero-dimensional fibers over certain of these orbits there, because the orbit down goes up as much as possible. And concretely, this means the following. And this is also worked out by Larson. So the clan V naught, avoids the following patterns, for SI in I. So you can't apply a reflection I if you have a pattern that looks like one of the following possibilities. So this bar is between I and I plus 1. So this is the I entry and the I plus 1 entry. The bar is just to tell us where these things are. So we can't have a sign and two numbers. I can't have two numbers and a sign. I can't have this, and I can't have this. So I have to, if I avoid those patterns, the resolution is small. So you can't put, there's some restrictions on signs between the two blocks that, again, to sort of be very concrete about this, what's happening is that V naught is equal to sort of this space V1 V2, it's got this kind of block decomposition. Your I, the possibilities for I they just occur in the spaces between that are between adjacent blocks. And then the condition is just on the entries on the ends of these blocks can't have certain patterns involved. Okay, so that's the theorem, the condition for it to be small. And then the theorem that the other part of this that we proved in our paper is that under the hypotheses above, actually we don't need the smallness condition, but we do need the commuting simple reflection. So mu from z v to xv as above has smooth and strongly reduced fibers. Okay, so maybe I'll pause for a second and see if there are any questions.
I think we're good.
Okay, so maybe just to comment on the proof. I mean, the proof is actually just it's actually involves using some relations between the k orbits on G mod B and the k orbits on some G mod P, and maybe I won't say anything more right now about it, but it's a little bit. One can sort of kind of understand these fibers pretty explicitly. The fibers are all homogeneous for some subgroup, in fact, so they're smooth, and then one can sort of show that just one can analyze the derivative well enough to prove this fact. Okay, so then maybe I'll just say a little bit more about this here. So it's, I guess it's, in this crowd, probably everyone is very familiar with the localization scheme that we would want to use to compute this push forward of these classes. But maybe I'll just say a word or two about it because there is a little bit of something to consider. So the basic idea now is to use localization on ZV to compute mu star of C of T of ZV capped with ZV. And what you would get is you would get an expression in terms of the fixed points here. So this is the expression in terms of this is in the equivariant Chow groups of the fly variety. And so here y is in, this is in terms of the fixed point. So we have to invert some elements. And then it's well known how to express YB as a sum of Schubert classes. Maybe I'll call it M of YW. Okay, now I've used X, so I need another letter for Schubert classes. Maybe I'll call it S of W. That's my Schubert variety there. And so then this gives us a formula for the equivariant Chern-Mather class of XV in terms of these P. And the only thing that it maybe is worth commenting on is that one has to be a little bit careful in computing the, to do this basically the T's on the tangent spaces TZ of ZV for Z in ZVT. Now, the only potential problem with this is that in principle, ZV is equal to this K V naught B closure cross over B PI mod B. And an algebraic geometer once told me that taking closure is like a very bad operation because you don't know what happens. And so the problem with this is it's a little bit non-explicit in that it's hard to, it's not completely clear how you would find the T weights on the fixed points at this space. So it turns out, however, that this can be rewritten a little bit, and I'll mention, just some sort of, in fact, I think that's interesting, and it kind of ties in with how we're using these Gmod Ps as well as the Gmod Bs. So we can get around this. Because what happens is that we remember I introduced at the very beginning, I introduced this invariant tau of V naught, which is the set of reflections such that V naught star Si is equal to V naught. And what happens is that we have this K V naught star B, this closure here mod B. This maps down to K V naught, its image in this tau of V naught mod P of tau of V naught here. But what happens sort of miraculously is that we don't need it when we do it down here, we don't need to take the closure. In other words, the image down here, if we call this map pi, the image of pi is pi is, the image of pi is a closed orbit. And so we can write K V naught dot B mod B closure. It turns out just to be K V naught P of tau V naught cross P of tau V naught P of tau V naught on B. And now we don't have to take closures of anything, so we can very easily compute the weights of the tangent spaces on this. And so we plug that in, we can get the weights of the tangent spaces. Okay, so then the only thing I will say is, maybe I'll just talk about I said we had some computational evidence, and it's not very large, but I'll tell you a tiny bit about that. So the example is, I want to take G to be GL4, and I want to take K to be GL2 cross GL2. And I want to take V naught to be this clan that looks like 1, 1, 2, 2. Okay? So here my I is going to be the reflection S2. V, which is V naught star S, is going to be 1, 2, 1, 2. In this case, tau of V naught is the reflections S1 and S3, and here tau of V is actually just the reflection S2. And the point is that in any event, so one can calculate this whole setup here. And if we look at ZV going to XV, what happens is that here, ZV, the T fixed points, that turns out there are 32 T fixed points. this orbit closure, it turns out, contains all the fixed points. So this contains xvt is equal to all the fixed points on the Flag variety, and so there are 24 t fixed points. And so if you do the localization calculation, what you get is that you get that Cm of t of xv, you get a sum of 24 terms because every t fixed point is in the image, so you're going to get every Schubert variety occurring in the image. And so it's a sum over, maybe I'll just call it C of VW of S of W, my Schubert classes here. And this is a sum over W, this is a V here. This is a sum over W and W. And the most complicated term is CV of the long element 4, 3, 2, 1. That's the long element of the vowel group. And it's alpha 1 cubed, alpha 2 squared, alpha 3 plus alpha 1 cubed, alpha 2 squared plus, there's about 50 more monomials, and plus 5 alpha 2, alpha 3 plus alpha 2 plus alpha 3 squared plus alpha 3. And all of those, and so you get rather large expressions, and all the coefficients are, and this is the most complicated, but the other ones some of them are also pretty complicated, and all the coefficients turn out to be positive. So even though this is not a very big example, it seems sort of impossible that this could be true, by chance. Let's put it that way. So I think it's 5:33, so I think I should stop. Thank you.
Thank you very much for a wonderful talk. Thank you.